I started by looking at what types of environments there were in mines, and I noticed that there were two typical environments, which really there were really two problem sets I needed to tackle that were obvious. There were a lot of long passageways, which were one-dimensional problems, as they're fairly narrow and not very tall. And then there were open chambers, which were more of a two-dimensional problem, as most things would tend to be on the ground floor. I selected an ultra wideband and time of flight transceiver for its improved resistance over a narrowband signal and signal string based methods. And it's more resistant to things like multipathing effects and narrowband noise and interference and propagation delays through materials. And some of the reasons why it's resistant to multipath effects is because it's a very short duration pulse, so they're less likely to converge and interfere constructively or destructively with each other. And it's a wideband frequency diversity, so the narrowband noise and interference sources are less likely to interfere with all of the frequencies that are associated with UWB. And then there's leading edge detection. So the very first signal that gets to the receiver is really the timer for the time of flight, and slower signals that are slowed down by a propagation delay or a multipath bounce are going to arrive later than that clear line of sight first reception, which is going to be your most accurate result. I used that Decawave UWB transceiver IC that I previously mentioned, and is included in the POSIX kit, which I ordered, which includes 4 anchors and 1 tag. The anchors are positioned around the area that you want to do your positioning, and the tag was connected to a Arduino Mega 2560 because it uses a Arduino pinout, and then via USB to my laptop, which is a USB to serial connection. And then on my laptop, I connected to it as a COM port. I wrote a few pieces of software to go along with this. 2 different sketches on the Arduino. The first one was a collect data sketch, which just collected all the ID position data, all the accelerometer, temp, mag, and the pressure sensor data from the tag and all 4 of the anchors, and reported all of that data over the USB connection to my laptop, so I could see the status of all of that. And I used that for initial testing. And then I had the distance stream application, which just streamed the distances from the tag to the 4 anchors. And then I wrote some C# code in Visual Studio on my laptop that parsed the streamed distance data from the anchors and came up with 2 different modes for it. The one-dimensional positioning to match the narrow passageway scenario that I described before, and then the 2-dimensional positioning mode to simulate a chamber. And the one-dimensional positioning node, the point only moves in the y-axis right down the middle, and it's done by calculating the distance between the nodes, and described more in detail in my paper. And then the 2-dimensional positioning, I used trilateration between 3 anchors at 0, 0, at some position x0, and some position 0, y, some distance from the 0, 0 nodes, and then moved around with the tag, and you can see the the point move around on the screen in the XY positions.
This is a demo of 1D positioning. I have the first anchor here plugged in, and then I have another anchor way down there on that corner with a battery. They're 13 meters apart. I have my board here, which is the moving position, and I have a program here showing the XY position. So I'm going to walk with the laptop here. So you see there's the position as I move closer to the, I'm going to walk now closer. So you see me walking closer to the point. You see the position marked there. So here now I'm at the other beacon right here, and you see my position is right by the top end here. This is the 2D trilateration test. So here's the 0, node. There's the way over there is the 13 meter node, and that's the X direction. And across the street over there I have the Y direction. There's a node at 14.7 meters. So looking on my graph here, that's the XYZ. So you see I'm there close to 0, node right now. So I'm going to walk towards the X node. So I should go along the bottom of the screen here as I get closer to it. See, I'm getting closer to it over here. Okay, now I'm at the X node here. I'm going to walk diagonally towards the Y node. So I should move diagonally across the screen. So I'm like way over there. I'm going to walk towards the 0, node. So here I'm getting closer to it, actually between the two, kind of. You can see as I move around on the chart here.
Some possible future hardware improvements are a custom tag PCB that you'll be able to get smaller, obviously, and incorporate all the parts. Be able to remove the IC that the POSIX board uses and not have to use their API and talk directly to the Decawave transceiver. Could also make, as I said, a lot smaller, lower power, etc. Could add Bluetooth or BLE connection to it to allow it to connect and stream data to a smartphone, and then possibly write an app for the smartphone. In addition to that, could do custom anchors with integrated battery and improved antenna that would just improve the performance of the anchor and make it a better package. And then you could have a mesh connection between the anchors that would allow you to pass data throughout the mine to allow networking of the position data of all the tags which are connected to miners. You could have a server in a safe location for disaster response, storage, and processing. That server could even be above ground. So if in case of a disaster, you could go review all the logs of position data and maybe sensor data. You could have additional sensors like toxic gas, oxygen levels, temperature, humidity, particulates, smoke, radiation. Those could all be in the anchors or on the miners or both, or they could be separate sensors. You could have buzzer lights or strobe. Those could warn they could be, if they were on the tag, they could warn the miner that there's some unsafe conditions detected. If there was a mesh network, they could even warn across the whole mine simultaneously to all the miners that there was something dangerous going on for quick response. And they could strobe or make sound to assist rescuers in locating miners. You could have a more optimized RF path and better antenna gains for longer range so you'd be able to space your anchors out more, or be able to space your tags out from your anchors more. And you could optimize for size, battery life, update rate, anchor spacing, reliability, and added features. Those are a lot of things that are needed still. Some possible software improvements would be three-dimensional tracking for challenging scenarios such as multi-level chambers, or to track in the up and down direction. And you could do that with the pressure sensor, or the some fusion with the pressure sensor and the accelerometer, or additional anchors to create 3D trilateration. And then you could use the Kalman, Madgwick, or Mahoney filter, or some other kind of filter, to combine the localization information that I already have with some of the other sensors to smooth it out, correct for errors, etc. You could integrate with this is what I just said. You could iterative based on past position data for error smoothing. Right now, my software is only reporting position data. It's recalculating on every loop. It's not remembering old position data and smoothing out errors. You could add mesh networking, communicate position data and other data, as I mentioned before, throughout the mine to other miners or to a server. You could test with interference and I need to test with interference in underground environment. So far, that has not been tested. Multiple tag support. So obviously, this would need to support more than just one tag, and the hardware is capable, but the software doesn't take that into consideration yet. And fault tolerance. There's no fault tolerance written in right now. There's no security written in, and quality of service would need to be added for a real system.